Alright, today we're going to talk about implicit differentiation. So, obviously we're talking still about deriving. I remember I told you we only do two things in this classroom. Take a derivative or take an integral. Right now, it's all about derivatives, okay? So what makes it implicit? Well, here's the thing. Since to this point we've done quite a few derivatives, but they've all been derivatives in the form of the function y equals f of x. And basically, it's a function that only has x variables in it, okay? Unfortunately, not all functions are going to look like this. For example, I have something like this, x squared plus y squared equals 1. So if you notice, I have two variables here. I have an x and a y now. So basically, guys, we're deriving, but I'm throwing a y in there. So that does change your process just a little bit. So what does this look like? If you recall, this is actually a circle. Let's pretend that that's a good circle. Okay, so it's a circle with a radius of 1. Okay, so it has a radius of 1. Um, think about what a derivative does. A derivative does tell me that the slope of a tangent line. So does a circle have tangent line? Yeah, a circle has an infinite amount of tangent lines, as a matter of fact. Pretend that goes to that. So could I take the derivative? Well, yeah, I can. Okay, so I can take the derivative just because it's a circle. Think about what it also tells you instantaneous rate of change. So um, as this is moving, can you tell me how fast it's moving? Sure. Think about what it also does, velocity of an object. So think about an object that's moving in a circle, for instance. I don't know, maybe a planet going around the sun, right, in a circular motion. Um, can you tell me how fast it goes? Well, yeah, I can take the derivative, okay? So how? How do I do that? Well, there's basically three steps, okay? There's three steps, and this is basically, it's an application of a chain rule, okay? It's a chain rule. So remember, the chain rule is the derivative of the outside with the original inside times the derivative of the inside. So here are the three steps. You're going to take the derivative of both sides of the equation. Notice that I have two sides. I have x squared plus 4, x squared plus y squared, and then I have 1. You're going to take the derivative of always. It's always going to be both sides. And we're going to use I told you when we learned about derivatives, it was either the prime or the ddx, right, which is a derivative with respect to x, okay? So you're going to take the derivative of both sides. So take the derivative of this, and take the derivative of this. So basically, um, take the derivative, let's do the right side. What's the derivative of 1? Well, the derivative of any constant is equal to 0. Take the derivative of this side. So just like before, I'm going to look at what's the derivative, each part separately. Derivative of x squared is 2x. And then here's the interesting part. What about when it's a y? So you're going to take the derivative of y like it's any x. So you're going to be able to use the power rule here. But the only difference is you're going to add a dy dx. Notice what this is saying. This is the derivative of y with respect to x. So basically, derivative of y squared is 2y. But then I'm going to add here this dy dx. And if you think about it, it's technically the chain rule. The derivative of the outside, so my power rule, 2y, and then times the derivative of the inside, which is the derivative of y with respect to x. Okay? So this is the only difference. Anytime you take a derivative of a y, take it normally, however you need to do it, most likely a power rule, and then just make sure you add a dy dx right next to it, okay? And then here's what we're going to be looking for. We want to solve for dy dx. I want to know what dy dx is. That's what I'm looking for. How do I solve anything? Get it by itself. All right, so here's where your algebra kicks in. How do I get dy dx by itself? Well, first, of course, I'm going to get rid of this 2x. So I'm going to have 2y dy dx equals to negative 2x. And then, of course, to get dy dx by itself, it's being multiplied, so I will divide. So dy dx is equal to negative 2x divided by 2y. Look at that's going to cancel, so what do you get? You get dy dx is equal to negative x over y. Remember, what did I just find? I just found, remember, slope of a tangent line. So the slope of this circle at any point on this circle, the slope would be a negative x over y. So think about what a point has. A point has an x and a y. So you could give me any point. I don't care what this is. Let's just pretend this is 1 comma 3. I don't know. It couldn't be, but it was 1 comma 3. So then the slope of this line would be a negative 1 over 3. Simple as that. Okay? So you're finding the slope of the tangent line at any point. Alright? Let's try another one. I have x cubed plus y cubed equals 8. Well, first, take the derivative of both sides. Take the derivative of both sides. Okay? Um, the derivative of 8, of course, is 0. Is this always going to be 0? Absolutely not. Okay? There might be some more variables over here. Okay? My point is you don't have to move them all to the left or all to the right. You could just take the derivative of both sides. So if there's variables over here on the right, just work them like you would normally. Okay? Over here, take the derivative. What's the derivative of x cubed? It is 3x squared. What's the derivative of y cubed? Well, again, I'm going to take it like as if it's an x, so it's going to be 3y squared, but because it's a y, I'm going to add my dy dx. And then, of course, get your x by itself. Or, I'm sorry, get this by itself. So, what am I left with? I'm left with 3y squared dy dx equals to negative 3x squared. Divide by 3y squared. So dy dx is equal to negative x squared over y squared. Okay? The 3's cancel again. Okay? So negative x squared over y squared. And that's it, guys. That's implicit differentiation. Derive like you would normally, but just solve for that dy dx that you added on every problem. So in the end, I want to know what dy dx is equal to. All right, let's try another one. Take the derivative of both sides. So I have 8x minus 18y, but because of that, dy dx equals to, derivative of 17 is 0. Okay? Get dy dx by itself. So I have a negative 18y dy dx equals to a negative 8x. And then, again, I'm going to divide. So I have dy dx is equal to a negative 8x over a negative 18y. Notice that those are going to cancel, so it's going to be positive. And then I can reduce this. So dy dx is equal to, I can reduce it, what, 2? So it'll be 4x over 9y. Again, what is this finding? This is the slope of the tangent line at any point x comma y. At any point on this, again, this is going to be a circle somehow, right? Or an oval, actually. This is going to be the slope of that tangent line. The instantaneous rate of change, the velocity of that tangent line at any point x comma y. Alright, we're going to kick it up a little bit. So I have y cubed plus y squared minus x squared equals negative 4. Again, notice I have two y's this time. I can't combine them, so I'm going to just do what I need to do. So take the derivative of everything with respect to x. So that would give me 3y squared dy dx plus 2y dy dx minus 2x equals 0. Okay? Again, I want dy dx by itself. So I have 3y squared dy dx plus 2y dy dx. And then I move that 2x so it equals to 2x. Okay? So again, here's where your algebra skills are going to kick in, guys. I want dy dx by itself, but notice I have two of them. So I don't need two of them, I only need one of them. So is there a way that I can make these one? Well, yeah. They both have one, so then couldn't I factor it out from both? Okay, so I can factor out a dy dx from both of them. If I did that, what's left? Well, then I have a 3y squared plus 2y equals to 2x. Well, look, now I only have one of them, and it's being multiplied by all this, so then to solve, wouldn't it be 2x over 3y squared plus 2y. There it is. The derivative of this function, whatever it is, whatever the shape is, at any point is equal to this. Okay? The next one's a little interesting. I'm throwing in some trig. Same rule. I do want you to notice, though, this is technically two functions. I have a function on the outside, which is sine, and I have a function on the inside, which is x over y. So this is actually going to be a chain rule. This is actually going to be a chain rule. Okay, so I'm going to take the derivative of the outside with the regular inside, then times the derivative of the inside. So notice, my dy dx isn't going to kick in until I take the derivative of the inside, because that's the only place it has my y. So, let's start with the regular chain rule. What's the derivative of sine? Well, that's cosine of my original inside, x over y, that's fine. And then it's times the derivative of the inside. But notice that I'm actually going to have to use the quotient rule for this one. What's my quotient rule? It's f prime g minus f g prime over g squared. Okay? So, I might run out of room here. Let's see. What's the derivative of the top? X. That's 1. Regular y, so 1y, minus the original top, which is x. The derivative of the bottom, which is y. Well, what's the derivative of y? Same thing as x. It's 1, but because I just took the derivative of a y, it's 1 dy dx. And then over y squared equals to, derivative of 1/2 is 0. Okay? So, here's what I have right now. It's a little crooked, but it's okay. So, it was chain rule. Derivative of the outside is cosine. Original inside times the inside, which I had to use the quotient rule on. Okay? So, look what I need to do. I need to get this by itself. I need this dy dx by itself. So, how? Well, first, does everybody agree that I need to get rid of this cosine of xy? It's being multiplied, so guess what I can do? I can divide both sides by cosine of x, y. Now, what's going to happen? If I divide this side by cosine of xy, it'll cancel. But 0 divided by cosine of xy is still 0. So I'm left with y minus x dy dx over y squared equals to 0 still. And now it's an algebra problem. How do I get this by itself? Well, it's being divided by y squared, so then I should multiply by y squared. Those will cancel. I'm left with y minus x dy dx equals to 0 times y squared, still 0. Now, guys, get dy dx by itself. So subtract your y, so x is negative x dy dx is equal to negative y. Dy dx is equal to a negative y over a negative x, which is, of course, positive y over x. So, looks like a complex issue. Can be very simple as long as you understand what you're doing. Okay, so recall, this was a chain rule. So the derivative of the outside, original inside, times the derivative of the inside, but inside I had to use the quotient. It wasn't too complex. The only thing is every time you take a derivative of a y, you have to add the dy dx. Do not forget that. And then it became a basic algebra problem. Okay, this one's a little bit more complex. Notice, I have two functions here. I have an x, and then I have an e to the x squared plus y. So this is actually going to be a product rule. But if you notice that when I try and take the derivative of this, it's actually going to be a chain rule. Okay? So, first, take the derivative of both sides. So, product rule. Product rule says f prime g plus f g prime. So this is my f. All of this is my g. So it's at this point where I'm going to have to use a chain rule. Okay? So, what's the derivative of f? Well, it's just 1. Right? So it's 1 times original g, so e to the x squared plus y squared, plus original f, so x, times the derivative of this. Now, this is going to be a chain rule. How do you take the derivative of this? It's going to be, it's exponential, so it's itself. So e to the x squared plus y squared times the derivative of the exponent here. So wouldn't that be 2x plus 2y? But because I took a derivative with a y, dy dx. And then equals to, what's the derivative of 5? 0. Okay? So this is where it gets interesting. Um, I want you to see that, see this, normally we put this up front. There's an x here. So you see that I can technically distribute this x to this. So I would have an e to the x squared plus y squared plus 2x squared plus 2xy dy dx e to the x squared plus y squared equals 0. Okay? So I need this dy dx by itself. So how on earth could I do that? Well, first of all, get rid of everything that I can. Okay? Does everybody see this 2x squared? It has nothing attached to it. So I can actually, whoops, I knew I made a mistake. So remember that it was actually this x is being multiplied by all of this. So it actually should have went to everything. Or this actually should have went to everything. So what you end up with is, I'm probably going to have to re-explain this one to most of you. So I have my this one, and I have my 2x squared. Basically what I was missing was, so this went to this, so I had an ex squared plus y squared, and then I had a 2xy x dy dx e to the x squared plus y squared equals 0. So notice they all have a and they all have an e to the x squared plus y squared. So because they all have one, I could factor it out. Right? Actually, no factoring necessary. So I want this alone. Get rid of these. So here's what you have. You have 2xy dy dx e to the x squared plus y squared equals to both of these. So it's a negative 2x squared e to the x squared plus y squared minus e to the x squared plus y squared. All I did was move these two things on the other side. Okay, again, I want this alone, so does everybody see that it's all being multiplied? So when I divide by a 2x, I'm sorry, that's not a 2. I would divide by 2xy e to the x squared plus y squared, which means I would need to divide this by a 2xy e to the x squared plus y squared. Okay? So those will cancel with that, and then this will cancel with that. So I'll be left with dy dx equals, well, the only thing that, so this has a 2x, right? But this doesn't, so I can't cancel. But what do they all have in common? They all have an e to the x squared y. So I can cancel that from everything. If I do that, what am I left with? I'm left with a negative 2x squared, and this doesn't go away. There's actually a minus 1 over 2xy. Okay? So this one's a little more complex because of the exponential, but you just got to remember that this x was technically distributing to everything, right? So this had to be multiplied by this first, and then the x went to everything. So there was two parts of this multiplication. The 2x plus 2y had to be multiplied by this, and then the x gets distributed, right? All right. Now, let's try another more complex one. Okay, let's try another more complex one. So notice here, it's going to be a chain rule. Excuse me. It's going to be a chain rule because I have an outside function and an inside function. Actually, it's two chain rules. I have an outside function and an inside function. Okay? And so let's take derivative of everything. What's the derivative of cosine? It's negative sine my original x plus y times the derivative of the inside. What's the derivative of the inside? Well, derivative of x is 1. The derivative of y is 1 dy dx. Do the same thing over here. What's the derivative of sine? It's cosine. Original inside times 1 plus dy dx equals to 0. So, here, what you have to understand is that this is being distributed. This whole thing has to be distributed to that. Same thing. This whole thing has to be distributed to that. So, negative sine of x plus 1 times 1 is negative sine of x plus 1. It's just itself. But then times dy dx is a negative sine of x plus 1 dy dx. Right? Same thing over here. It's a cosine of x plus 1 times 1 is cosine of x plus 1, x plus y, plus a cosine of x plus y dy dx equals 0. So, algebra problem. You want dy dx by itself. First, get rid of everything that doesn't have a dy dx. So in our case, we're left with a negative sine of x plus y dy dx plus cosine of x plus y dy dx equals to, I'm going to send this and this to the other side. So that would make it a positive sine of x plus y and a negative cosine of x plus y. I have two dy dx's. I only want one, so what can I do? I can factor it out. So I have dy dx. What am I left with? A negative sine of x plus y plus a cosine of x plus y equals sine of x plus y negative cosine of x plus y. It's being multiplied, so dy dx is equal to this divided by this. So sine of x plus y minus cosine of x plus y divided by a negative sine of x plus y plus cosine of x plus y. That is a y right there. Now, does this look familiar? These are basically the same equation. It's the same equation except opposite, right? So if you were the same thing divided by itself, but one's positive, one's negative, negative 1. So dy dx is equal to negative 1. So what does that mean? That means that at every point on this function, at every x comma y, doesn't matter what it is, its slope of a tangent line is always going to be a negative 1. Okay? Alright. Let's keep going. So here's where it actually gets useful. Okay? So, can I apply my implicit differentiation rules? Okay? So, can I find an equation of a tangent line at the point 1 comma 1 on the curve? Okay? So, notice now I have two sides of this. You see how I have two sides of this? So remember how I told you it wasn't always going to be equal to 0? Well, here's one of the cases. Okay, here's one of the cases. It's not going to be equal to 0 on the right side because you actually have an equation. So, how do you write an equation of a tangent line? Well, you need two things. All right, you need at least a point. So we have two formulas technically. We have the f of a plus f prime of a x minus a. So that one's easy. Or we also have that y minus y1 equals m times x minus x1. Now, how would you know the difference? How do I know when to use the f of a1 or when to use this one? Here's the difference. What do you need for this equation? You need two things. You need an x and a y, and you need a slope. Okay, you need an x and a y, and you need a slope. So right now I don't know my slope, but I do know my x and my y. So that's why I would say, well, use this equation and not the other one, because the other one, you have to find the y. In this case, they already gave it to you. Okay, so I need a slope. How do I find the slope? Well, slope is a derivative, so I need to take the derivative of this. So, take the derivative of both sides. The derivative of y to the fourth power is what? 4y cubed dy dx, because it's a y, plus, notice here, it's a product rule. It's a product rule because there are two functions. You have an f, you have a g. So it's actually a product rule just for this. So the derivative of the first part is 1 y plus x dy dx equals 2. Take the derivative of the other side. Wouldn't that just be a 3x squared minus 1? Again, I have 2y d, I have 2, well, first of all, get rid of everything that doesn't have a dy dx. See this 1y? Get rid of it. So I have 4y cubed dy dx plus x dy dx equals to 3x squared minus 1 minus y. Factor dy dx from both. That leaves me with 4y cubed plus x equals to 3x squared minus 1 minus y. Get dy dx by itself. Dy dx is equal to 3x squared minus 1 minus y over 4y cubed plus 1. Remember, this represents the slope of a tangent line at any point. So this is the slope of a tangent line at any point. More specifically, the point 1, 1. So it would be 3, 1 squared minus 1 times minus 1 minus 1y over 4 1 cubed plus 1. So notice, this is my x, this is my y, this is my y, because I know what those are. So you put this in your calculator, or you can just do it in your head. 1 cubed is 1, times 3 is 3, minus 1 minus 1. That's a 1, over 1 cubed is 1, times 4 is 4, 4 plus 1 is 5. So I have a slope of 1/5. So I know my slope, I know my point, I have my formula. So wouldn't this be y minus 1 equals to 1/5 x minus 1? Okay, well, give me a y equals mx plus b. So this would be y equals, or y minus 1 equals to 1/5 x minus 1/5. Add 1 to both sides, so y is equal to 1/5 x plus 4/5. The question was, find an equation of a tangent line at this point. Well, there it is. Okay, I'm going to have to move kind of quickly. I'm running out of time here. Same, uh, last one. Great. About 5 minutes. So, same question, same thing. What do I need? I need two things. I need a point and a slope. Okay, I need a point and I need a slope. I have the point. I have this formula. So I need to take the derivative. Okay, take the derivative of this. So, notice on the left side and the right side I have y's. So, the derivative of the left side. Derivative of this one's a chain rule. So, it's itself times the derivative of this. Wouldn't this just be 1 minus dy dx? Right? And on the right side, wouldn't that be 4x minus 2y dy dx? Okay? Notice that this is being multiplied to both, so it would be e to the x minus 1, minus y, minus e to the, let me put the dy dx up front actually, minus dy dx e to the x minus y. equals 4x minus 2y dy dx. So again, I want my dy dx's on the same side together, and everything else on the other side. So couldn't I move this over here and bring this over here? So that would give me a what? A positive 2y dy dx minus dy dx e to the x minus y equals a 4x minus e to the x minus y. Factor out a dy dx. That would leave me with 2y minus e to the x minus y equals 4x e to the x minus y. That would leave me with dy dx equals to 4x, this is a minus e to the x minus y over 2y minus e to the x minus y. And again, minus y, I keep saying minus 1. And again, you have your point, 1 comma 1, so this is your slope, your m, equals, wouldn't it be 4 times 1 minus e to the 1 minus 1 over 2 times 1 minus e to the 1 minus 1. 1 minus 1, of course, is 0. 1 minus 1, of course, is 0. So this is e to the 0. Anything to the 0 power is 1. So this is really just 1. So I have 4 minus 1. Same thing on the bottom. E to the 0 is 1. So 2 minus 1, which is 3 over 1, which of course is just 3. So my m is 3. So my slope is 3. You have my slope, you have your point. Y minus 1 equals 3 times x minus 1. Y minus 1 equals 3x minus 3. Y equals 3x minus 2. So what's the equation of the tangent line at a certain point? Well, there it is. Okay? So implicit differentiation. The only difference now with implicit differentiation is anytime you take a derivative of a y, you treat it normal as if it were an x, and then you add your dy dx. Okay?